All right, folks, so now we're going to get into our discussion of principal component analysis in earnest. So what we're going to cover in this video is going to be looking at this maximum variance formulation. There's going to be several ways of deriving PCA. We're going to start with this one. Okay, so let's get into it. So PCA is a technique that is widely used for applications such as dimensionality reduction, data compression, feature extraction, data visualization. So you might have already used this. Very useful tool, very good to know about. Always, when you're looking at data, probably the very first thing you might want to do with high dimensional data, do PCA on it, see what your data looks like. It's also known as the Carhoonen-Loew transform, and I believe this is more in the context of when you're working with like stochastic processes, but it's basically the same idea, exactly the same idea. Okay, so as he says, there are two commonly used definitions of PCA that give rise to the same algorithm. Now it says PCA can be defined as the orthogonal projection of the data onto a lower dimensional linear space, known as the principal subspace, such that the variance of the projected data is maximized. So that's the first one we're going to be talking about. Equivalently, it can be defined as a linear projection that minimizes the average projection cost, defined as the mean squared distance. Okay, so I don't think this is actually equivalent. So we'll see why, but basically it'll be because when you do this linear projection into that space to minimize when you want to minimize the projection cost, you can kind of rotate. You can rotate your coordinates in the space you're projecting into, and you'll still get the same projection cost. So there's kind of a redundancy in this approach. You can pick the same solutions as you do in the maximum variance situation, but there's going to be kind of redundancy there. So I don't think these two approaches are equivalent, but they're kind of very closely related. Okay, and we'll see that as we go. Okay, so let's start. So in this section, we're going to actually just be talking about the maximum variance formulation. So let's see how we do that and how it kind of gives us, our principal components. Okay, so consider a data set of observations x of n, where n goes from 1 to capital N. And x of n is a Euclidean variable with dimensionality d. So this is kind of your extrinsic dimensionality, your ambient dimensionality, data dimensionality, however you want to call it. Our goal is to project the data onto a space having dimensionality m less than d, while maximizing the variance of the projected data. Okay, so, and for the moment, we shall assume that the value of m is given. Later on, we'll figure out how to actually come up with that. Okay, so consider the projection onto a one-dimensional space. We can define the direction in using a d-dimensional vector u1, which for convenience, we shall choose to be a unit vector. Okay, so we're only interested in the direction because we're going to project our data onto that direction. So, for example, if u1 wasn't a unit vector, well, then all of your had some scale, a, well, then all your variances would all be scaled by a squared. So it's just kind of convenient to just and you won't there's no loss of generality as long as there's no loss of generality as long as so we might as well just choose it to be a unit vector. Okay, so each data point is then projected onto a scalar value u1 of t x of n. So we're just so let's just what does that look like? So here is our point cloud of data points. Here is our direction u1, and it's a unit vector, and we just take a data point and we just project it onto its projection along that direction. The mean of the projected data is u1 of t x mean, because this is just a linear operation. So if you take the mean of this, well, u1 is constant, so you end up just getting the average of the x of n, which gives you that. Where x hat is the sample set mean given by this, of course. Okay, and the variance of the projected data is given by, this is the data itself, this is its mean, and it looks like this actually. So it's actually the projection of the overall covariance along a particular direction. And so in case you don't see where this is coming from, so this is just the same as, make sure you guys can see this. So this is 1 over n times the sum. So that's going to be, if we look at that, that's going to be u1 transpose xn minus x. And he's kind of squaring that, and you can just write this as u1 transpose x of n minus x, and then you can write you can write A transpose B as B transpose A, right? So we'll just flip this around, u1, and then this will just be u1 transpose 1 over n times, xn minus x, xn minus x transpose. Running out of space here. There'll be a u1 hanging out there. But this thing is just, you can see this is just your data, the covariance of your data. So that's just that. Okay, so what we're saying is, for given a unit vector, or whatever it is, the projection of the variance along that direction is just you take the covariance matrix and you just project in this way along that direction. And notice, for example, if u1 was like the first elementary, whatever it's called, the first element being 1, all the rest being 0, well, then you would get the variance of the first variable, so on for all the others. But of course, in general, u1 will have more interesting structure, and it will just, you can get the variance along whatever direction you're interested in. Okay, so now that we've got this for whatever direction we're interested in, we maximize the projected variance with respect to u. So that's all it is. So now, okay, so clearly this has to be a constrained maximization to prevent the norm of u1 going to infinity, right? The same thing we were talking about before. You can maximize this variance by scaling u1, but that's obviously not what we want. So we're going to just have this normalizing conditions, this constraint. To enforce this constraint, we introduce a Lagrange multiplier that we shall denote by lambda 1, and then make an unconstrained maximization of this particular problem. Okay, so here's the thing, we're trying to maximize this, subject to the constraint that the norm of u1 is equal to 1. By setting the derivative with respect to, so now we just do the obvious thing. We're going to take derivatives with respect to u1, set them to 0. We see that this quantity will have a stationary point where this relation holds, and of course this is an eigenvalue relation, an eigenvalue equation. So we're saying that if we take the covariance and multiply it by u1, what's going to come out at a stationary point of this is that u1 itself scaled by some amount. Okay, so that means that any of the eigenvectors of S are a solution to this, but we want them. So how do we find the one we actually want? So what we say is, well, if we left multiply by u1t and make use of this constraint, we see that actually, so this quantity we were after, that variance is actually given to us by the eigenvalue. So the variance will be maximum when we set u1 equal to the eigenvector having the largest eigenvalue. So this makes lots of sense because, for example, for data like this, you've got, this will be your first, oops, let me just draw it slightly more cleanly. Okay, so here it is. We've got that, and here's your first eigenvector, and that's kind of what this will find. Okay, so now we can define additional principal components in an incremental fashion by choosing each new direction to be that which maximizes the projected variance. So we've already done that amongst all possible directions, but orthogonal to those already considered. So like we've already got one, and now we look at, okay, so now let's look at the next best direction that's perpendicular to the ones we already have. And if we consider the general case of an m-dimensional projection space, the optimal linear projection for which the variance of the projected data is maximized is now defined by the m eigenvectors of data covariance matrix corresponding to the m largest eigenvalues. And one way to just think of that, I mean, it might be already intuitive, but you can imagine, okay, we've projected our data along this direction, and now we're looking for the next direction that's perpendicular to that. So what we can do is we can actually take our data, subtract out the projection along that dimension. So now all we're left with is everything in all the remaining dimensions, and then do the PCA thing again, and now we'll get a new direction, and we just repeat that process. And you can see how that will just generate just this, each the corresponding eigenvectors, and in decreasing order of eigenvalue. So that's kind of maybe one way of thinking about it. And this is easily shown by proof by induction. So to summarize, principal component analysis involves evaluating the mean and the covariance matrix of the data set, and then finding the m eigenvectors of S corresponding to the m largest eigenvalues. And there's various ways of doing this. The computational cost of computing the full eigenvector decomposition for a matrix of size d by d is O d cubed. If we plan to project our data onto the first m principal components, you might not care about getting all d of them. We need to find the first m eigenvalues and eigenvectors, and you can do this with something like called the power method, or we can use the expectation maximization algorithm, which we will see later. Good, so I think that's all we need to talk about in this section. We do just a very simple thing, project along the dimension. We're interested in compute the variance, and then maximize that, and it turns out that will just give us the eigenvectors and eigenvalues of our covariance matrix. So I think that's all. I think one thing that's actually just worth noting is that, well, why do we care about maximizing the variance? We don't necessarily. It just seems like it's kind of just a good first assumption that, if you have a data set, kind of an ellipsoid data set, and you want to kind of compress that, or find interesting directions in that data set, the direction along which most of the variability happens is kind of a good bet. But it's not often the case. So sometimes, and we'll see it, I think he's got an example of it as well. But let's say you're actually not in this unsupervised setting, but you're in a supervised setting, where you actually want to distinguish two data sets. And the direction of their variance might not actually be the direction that maximally separates them. So you're not necessarily always interested in the maximum variance directions, but as a first pass, if you want to kind of summarize your data, it seems like a good assumption. So yeah, so that's kind of maybe a little bit on why we care about things like variance. Good, so hopefully that was useful. Please let me know if it was or it wasn't. Comments are always welcome. And I will see you next time when we talk about the related formulation, which is the minimum error formulation of PCA. So hope to see you then. Bye.